Hello, I'm Haneul Kim from AAAI XRLab. So today I'll introduce SkillTree, Explainable skill-based deep reinforcement learning for long horizon control task, which was accepted to AAAI 2025. So this is motivation. Deep reinforcement learning, or we can call DRL, is already very powerful. It performs remarkably well in games, robot control, and visible navigation tasks. However, since DRL mainly relies on deep neural networks, it often is considered a black box. We can't really understand why the model makes specific decisions. So this becomes a serious issue in safety-critical domains like autonomous driving, where humans must be able to interpret the agent's policy before they can trust or deploy it. So to address this, the field of explainable reinforcement learning has emerged. There are two main directions in XRL. The first is intrinsic explainability, which designs inherently interpretable models from the first start. The second is post hoc explainability, which adds explanation after training. Among these, the decision tree is an intrinsic model because its decision path is visible and easy to debug or verify. However, decision tree-based methods still face major limitation when applied to complex environments. For long horizon tasks, the trees become too deep and hard to optimize. For high-dimensional states, they struggle to represent the space effectively. And for continuous action, such as robot arm control, they cannot produce smooth actions due to the limited number of left nodes. To overcome these issues, the key idea of this paper is don't apply a decision tree directly to the action space. Instead, first compress the continuous actions into discrete skills and let the decision tree operate at the skill level. In this way, the tree maintains interpretability through discrete selection, while a neural network handles continuous control underneath. So this is the main contribution of this paper. First, they propose SkillTree, a novel hierarchical skill-based method for explainable reinforcement learning. Second, they introduce a method for discrete skill representation learning, which effectively reduces the skill space and improves the efficiency of skill-based policy learning. So experiment results across a variety of robotic manipulation tasks demonstrate that their methods provide skill-level explanation while achieving performance comparable to neural network-based approach. Before going into the details of SkillTree, I'll briefly go over the concept of the soft decision tree used in this method. So in a traditional hard decision tree, each node makes a binary decision, the right side. For example, if x1 is rather than 2, go left, otherwise go right. But in a soft decision tree, we can see in the left side, instead of a hard split, we use a probabilistic decision based on the sigmoid function. So each node has two parameters, a weight and a bias. They are multiplied with input vector x, and the result passes through the sigmoid function. This gives the probability of moving to the left or right child node, so the tree outputs a soft path rather than a fixed one. We use this structure because it combines the interpretability of decision tree with the learning capabilities of neural networks, which allow us to train the model using gradient-based optimization while keeping the decision paths explainable. Now let's move on to the methodology of SkillTree. The key idea is to make decision trees applicable to complex, long horizon control task by introducing discrete skill embeddings. In reinforcement learning, long trajectories can be hard to model directly. So, instead of predicting each low-level action, we convert a sequence of action into a short skill unit, which represents a meaningful behavior segment. For example, grasping objects or opening a drawer. So these skills become the basic units that the decision tree will later select from. So this one. Each trajectory is split into short segments of fixed length h, and each segment is encoded into a latent vector ZE using an encoder network. Then, from a predefined codebooks, we pick the closest entry to this vector. This quantized vector ZQ represents the discrete skills. So this idea is that a skill is only meaningful if it can reconstruct the original action sequence, which we ensure using a decoder that predicts the original actions from the state and skill vector. We also introduce a skill prior, which predicts the skill distribution given the first state of sequence. This helps guide exploration in reinforcement learning and prevents the policy from randomly sampling uninformative skills at the start of training. So in summary, the discrete skill embedding learning stage transform continuous action sequence into compact, reusable, and interpretable skills. These skills make it possible for the decision tree to operate in a discrete space, maintaining explainability while still handling complex, continuous control tasks effectively. So, this is how the encoder and decoder are trained. The architecture here follow a VQVAE. We can call vector quantized variational autoencoder, so which allow us to learn discrete skill embeddings. During training, each trajectory segments consisting of several consecutive states and action is passed through the encoder. So the encoder produces a latent vector ZE, which captures the essential patterns of that action sequence. Then we find the nearest entry from the codebook, and that quantized vector ZQ becomes the final discrete presentation. So the decoder then take the current state and skill vector ZQ as input and tries to reconstruct the original action sequence. By minimizing the reconstruction error, the decoder ensures that each skill can accurately reproduce its corresponding behavior. So, the total training rows consist of 4 parts. The reconstruction rows, this ensures the decode's actions are close to the original one, this one. And the second, codebook regularization, this one keeps the encoder outputs close to the discrete codebook entries. And third one is commitment loss. This one prevents the encoder from switching between different codebook vectors too often. Last is skill prior rows. So this aligns the skill prior's prediction with the encoder's output, so the model can later predict likely skill given the state. So together, these components allow the systems to learn a set of meaningful, reusable skills that can be clearly distinguished and later selected by the decision tree. Okay, now that we have learned the discrete skill embedding, so next step is to train a high-level policy that decides which skill to execute at each stage. So in this stage, every H step, the high-level policy is executed once. It outputs a categorical attribution over the discrete skill index k. Then one skill index is sampled, and the corresponding skill embedding zt is retrieved from the codebook. For the following H step, the lower level policy which we trained earlier take over. So this is the decoder. It used this skill embedding to generate the actual low-level actions that interact with the environment, resulting in the next stage, and the reward signal from the environments. The overall objective is shown in this equation. It aims to maximize the total expected reward over the trajectory, while also minimizing the KL divergence between the high-level policy and the skill prior. This is high-level policy, and this one is skill prior. So this KL term acts as a regulator. It ensures that the policy doesn't deviate too far from what the skill prior suggests, so which helps maintain stable and efficient exploration during reinforcement learning. So in short, this stage teaches the decision tree how to select the most appropriate skill at each step, balancing between maximizing the task reward and following the skill uses pattern learned from the offline data. So let's talk about how skill trees actually trained using reinforcement learning. So we use a modified version of soft actor critique, you can call SAC, but instead of a neural network policy. Now our high-level policy is implemented as a soft decision tree that selects discrete skill from the codebook. First, let's go over the main components. This one is the high-level policy. It's a probabilistic soft decision tree that outputs a skill index KT. And this one is a codebook of discrete skill embeddings learned in the first stage. And this one is the critique that estimates the value of each state skill pair. And last one is the skill prior that regularizes the policy to stay close to the learned skill dispersion. And finally, there's a replay buffer to stay close that stores experience tuples for training. So first is line 3 to line 8. This one is environment's interaction pace. So during its training iteration, they interact with the environments as the follow. So the tree policy sampled a skill index given the current state, and the corresponding skill embedding is retrieved from the codebook. The low-level policy then executes this skill from each steps. So in other words, the same skill dives several consecutive actions leading the environments to the new states. The resulting tuples is where the resulting tuple is stored in a replay buffer B, and this completes the data collection pace. The second one is line 9 to 17. This one is learning pace. So next, we sample transition from the replay buffer and update both the policy and the critiques. So we sampled from the bubble, and the policy produced the next skill distribution, and then they compute the target Q values, this one, so which includes the reward term and KL divergence term between the policy and the skill prior. So this KL terms ensure that the policy doesn't deviate too much from the prior, improving stability and exploration. So the critique is updated to minimize the MSE between predicted and target Q values, and the policy is updated to minimize the maximize expected return while keeping the KL terms small. So the temperature parameter alpha is automatically tuned so that the average divergence stay near a target value. Finally, the target Q network is softly updated using the rate tau, just like in standard SAC, this one. In summary, this process teaches the decision tree policy to select the right skill in each state by maximizing rewards while respecting the skill distribution learned from offline data. After the high-level policy is trained, they perform a distillation step to make the model more interpretable. Up to this point, the high-level policy is a soft decision tree. It performs very well, but because it is probabilistic, it can still be difficult for humans to interpret directly. To address this, they convert the soft tree into a hard decision tree. They reframe this distillation process as an imitation learning problem. So here, the trained soft tree acts as an expert, and a smaller, hard decision tree is trained to mimic its behavior. To do this, multiple trajectories are sampled from the soft tree policy in the environment. These trajectories are then used to train a CART, classification and regression tree model, using supervised learning. The depth of this distilled tree is intentionally limited, typically between 3 and 6 levels, to keep it simple enough for human understanding while still maintaining good performance. As a result, this distillation step preserves the decision logic of the soft tree, but significantly reduces model complexity, providing a finer high-level policy that is both effective and fully explainable. So this is the benchmark used to evaluate SkillTree. So they test their methods on 4 long horizon robotic control tasks with sparse reward, which are designed to measure how well the model can handle complex sequential decision making. So first is the Franca catching control task from D3RL. The environment uses a 7 DOF robotic arm that can interact with various objects in the kitchen. So among the two variants, MKBL, this one, is relatively easier, while MLSH is more challenging due to its higher task diversity. Second is, the third one, is cabin robotic arm manipulation task. The robot must execute a sequence of fine-grained subtasks like opening a drawer, toggling a light bulb, or sliding objects in a specific order. The finally is a office cleaning task involves a 5 DOF Widow X robotic arm that needs to pick up several objects and place them into corresponding containers. Because of the large state space and complexible object manipulation, this task is considered the most challenging among the 4. This is the baseline that they compare SkillTree with. The first is SBIRL, learns continuous skill embedding and a skill prior. It performs strongly but lacks explainability since it uses neural networks for both level of control. Second one discretizes the skill from SBIRL, but still relies on a neural network as the high-level policy. So it remains a black box model. Third one is behavior cloning plus soft actor critique. So this combines supervised imitation learning from demonstration with reinforcement learning fine-tuning. Finally, CART is an imitation learning approach that uses a decision tree trained to mimic a pre-trained SBIRL agents. Let's look at the main experimental results. This plot shows the downstream task learning curves for SkillTree and the baseline, averaged over 5 independent runs. On the x-axis, we have training step, and on the y-axis, the obelisk number of successfully completed subtasks. For example, action like grasping a cup or closing a door. So in the kitchen MKBL task, the top 3 methods converge at similar speed, and a SkillTree achieves the same final performance as the state of SOTA. In the more difficult kitchen MLSH task, SkillTree shows faster early stage learning compared to the baseline. And in Calvin, SkillTree and VQ SPILL perform similarly overall, but SPILL show higher variance and less stable learning. This one. Finally, in the office cleaning task, SkillTree's learning curve rise quickly and then converge smoothly, demonstrating stable and consistent performance. So across all environments, SkillTree matches or even surpasses SOTA methods while maintaining lower variance, which indicates more stable and reliable learning. This table summarizes the quantitative result in terms of average completed substacks and the number of leaf road in each model's decision tree. So in the kitchen MKBL and MLSH task, SPIRL and SkillTree perform comparably, while Calvin and Office SkillTree outperforms SPIRL, showing more stable performance. And you can see this SkillTree and DC plus distilling additionally applies data cleaning, keeping only high success trajectories before retraining the smaller tree. As shown, this boson achieves a highest ACS value across most environments, indicating that the distilled and cleaned model maintains high interpretability without sacrificing performance. So in short, SkillTree not only matches the SOTA, but does so with a compact, explainable structure. So this is the experiments that show explainability. This figure shows a depth-3 SkillTree trained with data cleaning and distillation. Even though the tree is very shallow, it still achieves an average of 3.03 successful substacks, which means the agent performs almost as well as the deeper models. This demonstrates that clear and effective decision-making is possible with very few parameters and a fully interpretable structure. Each node in the tree corresponds to a decision based on features such as QPOS, which represent the robot arm's joint position, and QPOS OVJ, which represents the position of the object being manipulated. And the number, this number next to the nodes indicates the branching threshold, and N shows how many state skill pairs fall under that condition. And in the color legend, each color represents a different skills. This one. So a leaf that is dominated by a single color, that means the agents behave consistently and predictably under that condition. Overall, the decision logic is fully visible, allowing humans to clearly interpret why the robot choose specific skills in different situations. This is how SkillTree learned interpretable skill-task relationship. This heat map visualizes how each learned skill corresponds to specific substacks in the environments. The x-axis represents the skill ID, and the y-axis represents the substack name. For example, interacting with the microwave, kettle, or button burner. You can see that the colors vary distinctly across tasks such as slide cabinets or hinge cabinet. This means that the certain skills are specialized for manipulating specific objects. Now, for instance, skill 8 to 12 mainly correspond to opening cabinets. This shows that the skills learned by SkillTree are not just random feature vectors, but meaningful and distinct behavior patterns that map to real, interpretable action in the environments. These figures show how the robot selects and executes skill over time during one full episode. On the x-axis, we have the time step, and on the y-axis, the skill index learned by SkillTree. Each yellow segment represents a period when a specific skill is active. We can see that the robot performs a sequence of tasks, operating the microwave, kettle, burner, and light switch by switching between different skills in a logical order. Interestingly, the same skill is often reused multiple times across different intervals, which suggests that each learned skill represents a stable long-duration action primitive. In other words, SkillTree decomposes the long horizon task into reusable, interpretable skills, showing how the robot's high-level planning emerged naturally from these learned components. To conclude, SkillTree propose a novel hierarchical skill-based explainable reinforcement learning framework designed to tackle the challenge of long-horizon decision-making in continuous control tasks. By combining discrete skill representation with decision trees, their methods provides a robust and interpretable solution that improve explainability without sacrificing performance. And experimental shows that SkillTree achieve competitive or superior performance compares to neural network-based baseline, while also offering transparent, skill-level explanation of the agent's behavior. However, there's still a few limitations. The low-level policy, which controls the actual motion of the robot, is still implemented as the neural network, meaning it remains a black box. We can understand which skill is selected, but not exactly how that skill is executed internally. Also, their methods currently depends on offline demonstration data, which can be a bottleneck for real-world application. So, as for future work, the next step is to make the lower-level control interpretable as well. For example, by integrating tree-based or rule-based decision model directly into the low-level policy, they could achieve a fully explainable reinforcement learning pipeline from top to bottom. Thank you for listening.